okay? So we are going to get 0.0020 meters, okay? Now we enter these values into a calculator. This is Q1, this is Q2, this is R. Make sure to square it, okay? That's very important. A lot of people forget that. And you should get that FC is equal to 56 newtons. So the force of attraction between these two, kind of giving it away. The question asks us one more question, and that is, in what direction do these particles move? Okay, right here, relative to each other. It's a small but important detail to note that these two charged particles are both positive. Okay, we're given 2.5 microcoulombs and 5.0 microcoulombs. It does not say negative, so we can assume that it's positive. Applying the rule that opposites attract, we know that these two will repel each other. As such, we know that they will move away from each other because a force of 56 newtons is exerted on both particles. So to kind of visualize what this is going to look like, let me clear up a little bit of space again. Nope. What happened? Okay, let me do that again. Sorry about that. Okay, I'm just gonna get rid of a little bit of space like that. That's all I'll really need. Okay, then let's set that back. So let's say we have our Q1 right here, and let's say we have Q2 right here, and this one here is positive, and this one here is positive. What this is going to look like is 56 newtons is exerted on Q2 due to Q1, and 56 newtons are also going to be exerted on Q1 due to Q2. These two then are going to move away from each other because they are the same charge. There we go. Okay. So that's where the particles will move relative to each other. I kind of gave it away a little bit when I mentioned that they were, when I started talking about attraction, but that wasn't even right. Okay, so the last thing that I want to talk about Coulomb's law, is the impact that distance has on the electrostatic force relative to the charges. Okay, so that's quite a mouthful, and I'll explain what I mean by that. Let's keep Coulomb's law there. I'm not going to need this picture anymore. I will just put, let's see, I'll just move this off the screen. There we go. Okay, so I'll say that one more time. I want to point out the relationship between distance and the electrostatic force relative to the relationship between the charges Q1 and Q2 with the electrostatic force. Okay, so it's important to note that the distance here is squared. Okay, distance is squared, while only each charge is only raised to the first. Okay, so let's say we have just some sample numbers. Okay, if let's say I don't know, let's say we're only changing the magnitude of Q2. We're only changing the value of it. Okay, so K and Q1 are constants. Okay, R squared is also a constant because it is not changing. Let's just say it's 1. Okay, so it's 1 meter. So when we square that, it's just going to turn out to be 1. And let's say Q2 is also 1. Okay? For this problem, just so we have some concrete values, let's replace this constant with 2. Okay? FC in this case would be equal to 2. If we doubled Q2 right here, okay, so let's say we put 2 and then kept everything else the same, we would get that the new FC is equal to 4. So what do we notice? Doubling the charge doubles the force. Okay? But what happens if we change distance? What happens if we change r? So now let's focus on changing just one variable at a time, and let's just change r. If we double r, okay, so k, q1, and q2 are all constants, so it's just c over r squared equals fc. And then let's say this constant up here is, I don't know, let's say it's 4, okay? And r, let's say, is 1 right now, okay? Just like it initially was, okay? Then we would get fc is equal to 4. But if we double the distance, okay, if we double r, what do we observe? Well, when we simplify this, we see that fc is equal to 1. Okay, so when we doubled r, the electrostatic force is 1/4 of the original. Okay, one more example. Oh dear, that is huge. Okay, so we have 4 up here, and let's say we tripled it. Okay, then what do we get? We get 4 over 9. Fc is equal to 4 over 9. What's the relationship? Well, when we tripled r, Fc is 1/9 the original value. Okay? The mathematical relationship detailed in Coulomb's law appears in other scenarios as well and has been called an inverse square law. This is because the electrostatic force varies with the inverse square of distance. Okay, so let's break that down a little bit because I know that sounds a little overwhelming initially. Inverse square. That basically means when the numerator is constant, okay, and let's say this constant, let's just say it was 1. Okay? Fc varies with the inverse square of r because it is 1 over r and r is squared. Hence, inverse square. Doubling distance doesn't double Fc, but rather has an inverse squaring effect. Fc is 1/4 the original value, as we saw just now. When r is 1, Fc is 4, but when r is 2, Fc is 1. Intuitively, this makes sense. Gotta clear out a little bit more space. When we move two charges farther from each other, the force of attraction becomes weaker and weaker. If you ever held two magnets really close to each other and tried to keep them apart, you'll notice that it's much more difficult than if you were to try to keep them apart at a farther distance. So if we held like a magnet right here, let's say that's north and that's south, and then we had one right here and that's south and that's north, these are going to have a lot of attraction between here, okay? And to try and hold them apart at this close distance is going to be very, very difficult. You're going to have to use a lot of force to keep them apart. But if they were farther apart, well, then keeping them apart is a breeze because the force of attraction is so weak between these two. All right, now let's consider one last problem. Okay. Oh, no, I don't want this one. Alrighty, so here's our next problem. If the original electrostatic force between two charges is 5 newtons, what is the new force if the distance is halved? Okay, if we have R, okay, we amplify Fc by a factor of 4. We saw that in the previous, we didn't see that, but that's what's going to happen. If you don't know where this number comes from, don't worry, we're going to go through it right now. Okay, so like we were mentioning before, the only variable that we're changing is r, okay? So the numerator essentially is just a constant. So this is just a constant. We know that FC is equal to 5. So we're just going to plug in some hypothetical numbers, okay? Just to make this, just to create a scenario where the force, the electrostatic force is actually 5, okay? For the electrostatic force to be 5 newtons, R then would have to be 1, okay? So this right here is our initial, okay? This is our original scenario. The denominator would be 1, so that the force is 5, but if we halved the denominator and used an R value of 1/2, we can then calculate the new force. Okay, so this is constant, and we are going to plug in 1/2. Okay, so here's where things can get a little bit tricky. Let's just simplify the denominator because we know that 1/2 squared is just 1/4. Okay. Having fractions and fractions can be problematic, but as long as you keep track of where the dividing line between the numerator and the denominator is, so this is the dividing line right here, that's the dividing line. As long as you keep track of where that is, you'll be fine, okay? If you somehow mistook this as the dividing line, then things are going to be a little bit different. Dividing by a number is the same thing as multiplying by its reciprocal. The reciprocal of 1/4 is 4, so we can express this same thing as 5 times 4. And we know that 5 times 4 is equal to 20. So 20 newtons is the new force. Once again, this makes sense. When we bring two charges closer and closer together, the strength of the force increases. Think about the magnet example that we were talking about. Okay, so that was just a brief overview of the math behind Coulomb's law, inverse square laws, and electrostatic forces, and I hope you found this video helpful.